We are at the PBOC Central Lab in Prudhoe Bay, Alaska this morning. We're going to walk you through the login process for our samples, oil and water and gas samples, and then later on we'll go through and explain each of the different areas and how the analyses are done. In this area here, we receive samples. The samples are logged into our LIMS system. It's called LabWorks. The samples are each assigned a specific lab number. That lab number follows the sample all the way through the process, all the way through the reporting process and into the database, and is searchable in the database by facility or by lab number and various other ways of finding the data. Once the samples are logged in and they're given a specific lab number, then they spread out through the rest of the lab. One of the first places we're going to go is the gas sample area. Gas samples are received, are collected in these gas cylinders. These gas cylinders have a back pressure. We back pressure about 30 pounds of vacuum. So when we go out to the field, we make a connection on this end, and we open the valve. The suction brings the sample into the cylinder. The cylinder is then shut off, and we have our sample ready to go. From here, the sample is brought in after it's logged in, and it's placed in our area here for heating. The samples are heated in the heating pad for about 2 hours at 140 degrees. This simulates the temperature of the bottom hole temperature, or the test separator temperature as it comes out of the hole. This is our gas chromatograph, and we use this to run gas analysis on all our gas samples. Essentially, we inject a gas sample into the chromatograph. It goes through a heated column in an oven and generates data after about 40 minutes. It takes 30 to 40 minutes roughly to run one gas sample. And essentially all it does is it heats up the gas and puts it into a gas state where the molecular weight of the different constituents from methane all the way to C9, depending on the weight, come out at different times on the chromatogram. The GC has a integrator that goes through and calculates the area under the peaks and generates mole percent data for that. And we also do NGL analyses. We're running some now these are primarily from CGF. In this area here, we do primarily flash points. Whenever there is a tank out at GCs or flow stations or wherever that need cleaned out, and a super sucker is going to do the job, we make sure that the flash point is within a certain range and there's not any issue with volatile hydrocarbons igniting. This area here is the main lab. In this area we do crude analysis, specific gravities. We do all the QC on the methanol that goes out to the different facilities. We also do some portion of water analysis, alkalinities in waters, and chlorides as well. We'll walk back through here later and explain a little bit more detail as we go through this process. This is our ICP. This instrument we use to do analyses on water, primarily cations, magnesium, strontium, iron. We do a lot of samples in this part of the lab. We also run an IC, which we use to do our sulfates and organic acids, and we also do chlorides. Right now we're waiting on an auto sampler to get it up and running again. But this completes part of the analyses, particularly for scaling tendencies. So we do all the cations, the ICP work, as well as the water work with bicarbonates and pH. And this helps to predict the scaling tendency of some of our produced waters. Our NALCO engineers are in charge of running that program. Next, we'll have some of our lab staff, Mr. Tim Finley and Mr. Tim Fitzgibbon, as well as Heidi will talk a little bit about their specific areas and their instrumentation and explain a little bit about how that works.
So my name is Tim Finley. I'm a chemist here in the lab, and I do a variety of things. I used to work in the crude section. I worked in the ICP, and then now I'm doing all this other stuff. This is over here is our UV vis instrument. That's ultraviolet visible, and so what we do is we will get crude oil samples that are in produced water samples that have crude in them, and we will use xylene to extract the crude. And so what we end up is something like this. We have something like this, which is the crude extract on top. And so we will take a portion of this and then we'll dilute it. It'll be something like apple juice, or it's a pale brown color, and we will obtain a concentration of the crude in the water. And so that's what this instrument does. This over here is our FTIR. This is it will give a fingerprint of compounds in the oil field, so that we're able to let the people know that if it's like anything from like methanol or toluene or bulk chemicals, that'll give us a good indication of what's there. So this, and then so what I'll do too over here is this is sample ready for what's called TSS, which is total suspended solids, and there's in a lot of cases this is mostly produced water. We'll have go through here and through a manifold and with a filter, and the object is to find out how much suspended solids are in produced water. So there's a lot of rock flour occurring over at GC2, and so they're interested in knowing things like that, and then there's a lot of little grit and sand that comes up from the wells, and they want to try to optimize their facility to see where the problems are. So that's what this is all about here. It's filtration. Over here, this is a automatic titrator. Okay, we will get samples in for alkalinity. The samples are mainly from Melanie Point, and there's other areas too in the field that have problems with scaling, calcium carbonate scaling. So when we'll get us maybe 60 samples in, and I'll just put them on a carousel. I'll prep them first, and then put them on a carousel, and then just what comes out is the alkalinity concentration for that. For those produced waters, mainly it runs like from 2,000 to 4,000 parts per million in some of the wells. Over here, I have a Carl Fisher moisture titrator, so I'll do bulk chemicals, I'll do TEGs. I'll get a lot of. Sometimes I'll get like triethylene glycol samples. They're TEG from facilities, like from all the facilities. And I might run percent water sometimes. Over here I'll run pH on them, and so pretty much all set up to run those two, and then sometimes I'll also run, so for a glycol, I'll run percent water, pH, and then sometimes I'll also run TSS again, and then also this here will give me the ability to run percent hydrocarbon in TEG. So here I'm working on a solid sample. This is material that came in from a facility, actually a well. They found that there was some material there that looks like this, and they want to know what it is. And so I'll first dry it with extraction, with toluene extraction, and then I'll use acetone methanol extraction, and then I'll have a let's see, I'll show you what happens. I have a filter like this, so I'll put that material in there, and then I just poured that out into there, and then I will run a pellet on it, X-ray pellet, and then I'll also run some other tests, which gives the loss on ignition, the acid insolubles and acid solubles on this solid material. So it's very helpful to those people that are interested in finding out what is the nature of a solids material that's an unknown solids material. This is a vapor pressure analyzer. It is used for finding the vapor pressure of crude that has been sitting around for a while, and they want to know what to do if they can dispose of it, so they need the vapor pressure. In 2007, the BP needed to have an instrument that would determine sulfur and diesel, because they were mandated by the federal government to use ultra-low sulfur diesel for equipment and for trucks, instead of the regular diesel at the topping plant. So as a result, they decided to install this instrument, which is it's a X-ray. What it does is it will it will take a cup. Okay, so I'll have a cup here, and I'll fill it full of diesel, just a little bit, and I'll put it in this cup here, and I'll put it in here, and then it'll lift it up, and then it'll go and run it, and we'll get a readout of the amount of sulfur in diesel. So then, as a result of it being, it's also can be used for other things besides that. This is, as I mentioned before, we had that pellet. So I made a pellet, and so I put it in the cup, I put it here, and I put it in there, and then it will, over time, it will go and run out, and we'll be able to determine all the elements we're interested in. So I can run through all elements from sodium on down to uranium, and so that way we'll know what's there. Usually I'll end up with things like iron and sulfur, with calcium, silicon, aluminum, those common elements. Those are very common oil field elements that they want to know. If it has iron and sulfur, that's a good indication that there's iron sulfide forming in the lines or the pipes, and that's a corrosion product or a byproduct of corrosion. So that's very useful information.
I'm Tim Fitzgibbon, oils chemist in this area, along with my alternate who's off slope. So in this area we do oils analysis, a lot of water cuts, how much water is the well producing, produced water versus how much crude. A good example of that would be, that's a relatively low water cut and that's a relatively high water cut. So you see the importance of that in dollars and cents and how effective the well is. And so when making adjustments, people want to know, how much water's there. We do a lot of samples, a lot of regularly tested wells that engineers are monitoring. So there's a lot of that. This sample that I'm working on right now is Endicott transit crude, and so we monitor the water in that and what's going down the pipeline. This sample will get mixed and I'll run it for percent water and API. For the percent water, we do basically a very crude analysis. The sample gets a couple of drops of emulsion breaker, depending on how the sample is in appearance. Some samples need more, some samples need less. They go through a water bath at 140 degrees until they're properly separated. And then what we're looking for is a good clean break in the sample. When they come in, usually right out of the well, there's just not that good clean break, so we make some effort to separate as much of the free water as we can from the crude oil. So we'll do just a rough analysis with a ruler, take the percentage of that, that's the bulk water, and then on the Carl Fisher's over here, it's very precise, and I'll add a small amount of oil to that sample, or to that instrument, and then it will do its thing and then spit out how much water's in the crude, and then essentially we add the two numbers together. Two types of water cuts that we do are essentially, we call them wet and dry. On the dry water cut would be something like this, where we separate as much free water from the crude as we can. On something like this, which doesn't have free water particularly, we're going to do a wet API, which means I'm going to mix the sample and then analyze it that way without any other efforts to remove the water. And so there's a big difference, and for something like this, it's very precise and need to know exactly how much water's in there. The other thing that we do then in relation to that is density with the densitometers here. It'll give us the specific gravity, the density for the produced water, as well as the crude and anything else that somebody needs a density or specific gravity on. So another thing that we do a lot of in this area is freeze protects. When a well's shut in, obviously you don't want the produced water in line to freeze up. Have had problems with that in the past. So when they freeze protect a well, they'll collect a sample, I believe, on the opposite end of where they're pumping to, and then they'll collect that fluid, dead crude, methanol, typically a mix. They'll bring it in, and then we're looking for a specific amount of freeze protection, and that's based on the amount of water. Essentially, if it's less than a certain percentage of water, you don't have to worry about anything freezing up. Otherwise, if there's a certain percentage of methanol, then we can estimate the amount of freeze protection based on the percentage of methanol. Another thing that we do in the oils section is viscosity. So a measure of obviously how thick the oil is. To do that, we use the Cambridge viscometer here. It essentially has a cylinder with different sized cylinder like this, which goes in this little cup here, and then radio frequency magnet will draw this up and down through the oil, and then the amount of resistance is based on the time it takes to travel, and it calculates the viscosity based on that. And basically we can run viscosity from 2 to 10,000 with this instrument, 2 being the lowest, very light range stuff, 10,000 practically being a solid. So, and that's it. We can do it at multiple temperatures. We have a water bath that circulates through the instrument, and we can set it for a particular temperature and then do it at essentially whatever temperature you need within limits on the low and the upper end. We don't have a good ability to match like well temperatures, and we do tend to have, if you just ask for viscosity, a set temperature that we typically operate at, so most of our data is at about the same temperature. So I have a sample mixed here, and I'll show you how we load the densitometer and just basically how it works. We fill the tube. Tube vibrates at established frequency, and that's based on then relative to the density of water. And so we'll do a water measurement every day and check that the instrument's working. So essentially then through whatever calculation that the instrument does, as the density of the liquid that we put in changes, the frequency of that tube vibrating changes. And so it's just a relationship of how the frequency changes. It essentially has to be a homogeneous liquid to put in there. If there's 2 phases, for instance, if I end up with an air bubble in there or some free water in a sample, then it'll err and I won't get a valid result. So we put a homogeneous sample in there, run it through the tube, and push go, and it spits out a result for us. Then on the Carl Fisher, it's a water titration, and there's 2 solutions in here, and as the reaction proceeds, it doesn't directly measure the water, but there's a 1-to-1 relationship in the reaction. So there's an anode and a cathode, and as the reaction occurs, it measures the amount of currents that is used, and then that's relative to the amount of I2 that is formed, and that is directly proportional to the amount of water in the sample. So we do this analysis by weight, and I have a worksheet here. If a sample's wet, it only takes a couple of drops. I know this sample is always particularly dry. We run it every day, so I put a fair amount of sample in there and push go. And again, you can see it'll do its thing as the reaction proceeds, and then once the reaction ceases, then the voltage drops to 0. The instrument's done, and then it does a calibration or a calculation, and then reports back how much water is in the sample. And that's it. Fairly simple, straightforward, and a physics lesson beyond that.
My name's Heidi, and in the metals section, we're running ICP-OES and also IC. ICP-OES is inductively coupled plasma optical emission spectrometry. We receive the sample. If it's an emulsion, we use an emulsion breaker and heat to break the water out of the sample. We then acidify the sample. The autosampler introduces it to the instrument, where it's nebulized into an argon plasma. It's an RF-induced plasma. It's about 10,000 Kelvin, which is roughly 18,000 degrees Fahrenheit, which is twice the surface of our sun. The liberated atoms are in an excited state. They're further excited by collision energies. When they start to drop back down to their ground states, they emit a photon. The photons are of a characteristic wavelength for each atom. The photons are collected and focused by lenses and mirrors, and then there's a very large prism that splits out the wavelengths. The wavelengths are then detected at a photodetector, and they run through a photomultiplier tube. And with the magic of electronics and computers, we receive a signal or see a signal at the end. Mostly we use this to monitor scale inhibitor treatments. An ICP analysis can be used as sort of a fingerprint. For instance, we can tell the difference between a Cretaceous seawater and the modern epoch seawater. OES is capable of running about or analyzing for about 70 atoms. However, we have a list of the 13 pertinent or applicable atoms here. We also run IC, which is ion chromatography. We used a positively charged column to separate out negatively charged molecules, sulfate and chloride in one method, and then organic acids in a second method, which we are looking for acetate, butyrate, formate, and propianoate. The column is flushed with a basic solution as the ions separate by charge and molecular size, and then they are flushed out by the basic eluent. And again, we see them on the computer as a signal.